In this video I will tell you guys about the Fresh Air Cfm calculation. So there I have opened the drawing for the school project. I will show you our different areas for Fresh Air Cfm calculation. So let's start. So first I will calculate the Fresh Air Cfm for this chemistry and bio lab. So in order to calculate the Fresh Air Cfm, I have made this Excel sheet as you can see over here. What we need over here is the room area, Cfm per square feet, number of persons and Cfm per person, and total fresh air will be the sum of Cfm1 plus Cfm2. So let's start for chemistry and bio lab. As you can see, the area of this chemistry and bio lab from here, this much is the width, 10.9 meter is the width of this lab, and 13.2 meter is the length of this lab. So area will be 8.4 times 13.2. That is 110.88 square meters. Also this area is also included, so this is 300, that is 3 meter by 1.6 meter is this area, plus 1.5 meter into 1.4 meter is this area. So that total area will also be added in the chemistry and lab, because this is the part of this chemistry and bio lab area. So let us add this area, that is 3 meter by 1.6 meter, that is 4.8 square meters, plus 1.5 into 1.4 meters, 4.8, 1.5 into 1.4 plus 4.8, that is 6.9 square meters. 6.9 square meters, plus we have already calculated that area, 8.4 into 13.2, 8.4 into 13.2, 110.88 plus 6.9. So total area is 117.78 square meters, but we have to put that area over here in the square feet. So in order to convert that square meters into square feet, we will multiply it by 10.76. so 1267 square feet is the area of this lab, 1268. Okay, now go for computer lab and classroom. So I will show you one more over here, that is computer lab. As you can see, the length of the room is 1.2 meter, 12 meters sorry, and width is about 8 meter. So total area will be 8 meter by 12 meter, that is 96 square meters, but we need to convert this into square feet, so multiply it by 10.76. so we'll get 1033 square feet, 1033 square feet. Now I will calculate one of the classroom also. As you can see, this is the classroom, and its length is 12 meters and width is 8 meters, so it's same as computer lab. So area will be same as computer lab. So let's move to the next column, that is Cfm per square feet. For this I have opened this HVAC software. If you will go to the spaces and then go to new default space, from here we can select the ventilation requirement as per HVAC standard 62.1. so what we have over here is science lab, that is chemistry bio lab. So if we'll scroll down over here, as you can see, education science lab, that is chemistry bio lab. So we can select this over here, and you can see the CFM per person over here is 10 as per X-ray standard, and CFM per square feet required for science chemistry lab is 0.18. So 10 CFM per person and 0.18 CFM per square feet. So 10 CFM per person and how much? 0.18? Yeah, 0.18 CFM per square feet. 0.18 CFM per square feet. As I have already applied this formula, this room area into CFM per square feet will get first CFM. You can see over here, this and this will get the CFM1, that is 228. Now how to get the number of persons? Usually from the architecture you can get the number of persons, how many persons will occupy this chemistry and bio lab and computer lab and classroom. So let's assume the number of persons in chemistry bio lab will be 15. So this CFM2 will be calculated as follow: this number of persons into CFM, you will get this CFM2. So total CFM, how you get this total CFM? Total CFM will be the sum of this first CFM, room area into CFM per square feet, plus number of persons into CFM per person. So total CFM will be CFM1, that is 228, plus CFM2 150. So total is 378 CFM for chemistry and bio lab. In the same way you can calculate the computer lab and classroom. So I will show you again. Let's go for computer lab. In the education, so there it is, education computer lab, you can select from here. So CFM per person is 10 and outdoor air requirement is CFM per square feet is 0.12. So this is 0.12 and 10 CFM per person, and we use the same number of persons here also. So again this CFM area of this lab into CFM per square feet will get CFM1, and number of persons multiplied by CFM per person will get CFM2, and total CFM for computer lab will be the sum of this CFM1 and CFM2, that is 273.96, 274 CFM. So let's calculate for classroom also. So this is the education classroom for grade 6 students. So let's go for classroom age 9 plus, and the CFM per person is 10 and CFM per square feet for classroom is 0.12. So it's again 0.12 and this one is 10 CFM per person, and number of person will take same, or we can check from architecture. So total CFM required for classroom is again 274. So if you need to calculate the total CFM for these three areas, chemistry bio lab, computer lab and the classroom, it will be the sum of these three CFM that is calculated over here is the sum. So this is how you can calculate the fresh air CFM for each and every room. So in the same way you can find the CFM for other classrooms. In this video I will tell you guys how to calculate the chemical quantity required for the chilled water system. So let's start. Here I have made an Excel sheet for chilled water system volume calculation. Before starting the calculation, I will explain you why for chilled water system chemical is required. Why do we need to put the chemicals? So we need to put the chemical because we need to prevent the system from corrosion, scaling, fouling and microbiological growth. We are doing this basically in three ways. First, the chemicals react with the pipes to form a protective thin inside layer. Second, the chemical help in maintaining the pH level, and third, the chemical remove the corrosive dissolved oxygen in the water. So we are using the dozing pumps to supply the chemicals in chilled water system. I will show you over here in the drawing. There I have one drawing for the chiller yard. There you can see that we have 4 chillers over here, 1 2 3 4, and this is the chemical dosing pot installed over here. Let me zoom in. So as you can see that this is the chemical dosing pot. We are using automatic and manual chemical dosing pot over here. So basically these dosing pots with the dosing pumps are used to supply the predetermined quantity of the chemicals at regular intervals. So as you can see, that is how this chemical dosing pot is connected with the chilled water lines. This is our basically chilled water supply line that is coming from the chillers, a chilled water supply, and this is our bypass line, and this chilled water is basically supplying from the chillers into the secondary chilled water pumps. Here there are 3 secondary chilled water pumps, and then this chilled water is supplying from here to the buildings, and similarly this chilled water is coming back to the chillers from the buildings through these lines, and then going into the primary chilled water pumps, and through this primary chilled water pumps it's returning back to the chillers, and the whole process repeats. So this is our chemical dosing pot installed over here, as you can see that. So let's start the calculation over here. So this is the Excel sheet. First you have to write all the piping you have used in your project over here, all the dias from your drawings, and then you can convert this into radius, this one in inches, and this column same radius, and it is in meter. You can use the conversion to convert this in meter. So this is all the piping we have used in our project, that is 1.25 inches to 14 inches. So you have to calculate the area of the pipe for 1.25 inches. Similar, it's like pi r square. You can calculate the area of the pipe for each and every dia. So let's move to the next column, that is pipe length. You can get this pipe length from your drawings. So 1.25 inches dia we have used 130 meter in our project, and 3.5 inches we have used 90 meters, and 8 inches we have used 30 meters, and 14 inches we have used 20 meters. So all of the lengths are given here. So now we have to calculate the volume for this pipe. So we know that area of the pipe is here, length is here. We just need to multiply this column with this column. We'll get the total volume to 1.25 inches dia pipe, which we have used in our project. In the same way you have to use for all of the pipes which you have used in our project. 14 inches, same way you need to multiply area times length, and you will get the volume through 14 inches pipe which you have used in our project with 20 meter length, that is 1.99 cubic meter. So now you have to sum all of these volumes, and you will get 11.89 cubic meter volume that you have used in your project. So the total chilled water volume which we have calculated is 11.89 cubic meter. So now we are going to use some safety factor, that is 20%. So we need to get the 20% of 11.89. So there is 2.37 cubic meter. The total chilled water volume becomes now is 14.7, simply 11.89 plus 2.37. So it is 14.27 cubic meter. Now the chemical which we are using over here is corrosion inhibitor, that is A0029, and the second one is microbiocide A2400. So this is a file from Waterbird Chemical Treatment, is one of the reputed company in UAE. So we are going to use the chemicals provided by this Waterbird Chemical Treatment company. So this is A0029 corrosion inhibitor chemical. As you can see that the concentrated liquid blend of corrosion inhibitor designed to control the wetting and corrosion in closed chill water system and hot water system. It will protect all commonly found in closed system from corrosive attack. I will send you these files and you can read it yourself. So the main thing, the dosage rate for A0029 system, how much is the dosage rate recommended by Waterbird Chemical Treatment. They are recommending 3 kg per cubic meter of system volume is required for your chilled water system. So A0029 corrosion inhibitor, we needed 3 kg per cubic meter of system volume. As you can see that the chilled water volume which we have calculated over here is 14.27 cubic meter. So 1 cubic meter required 3 kg as per recommendation of Waterbird Chemical Treatment. So how much chemical we need for our system? Because we have 14.27, we simply need to multiply this quantity with this quantity. So we need for our system is 42.81 kg of A0029 corrosion inhibitor chemical. Similarly, we have another chemical we are using over here. This is recommended by Waterbird Chemical Treatment, that is microbiocide A2400, and this is the description and advantages. So the dosage rate recommended by Waterbird Chemical Treatment is 100 ml per cubic meter of system volume. So our system volume is same 14.7. We just need to multiply this 14.7 with 100 because 1 cubic meter requires 100 ml. So 14.27 multiplied by 100 will get the chemical needed for our chilled water system, that is 1427.28 ml of microbiocide A2400 is needed for our system, chilled water system. So this is how you can calculate the quantity of the chemical required for the chilled water system, and we are using these dosing pumps to supply these chemicals into a chilled water system. So I will tell you guys how you can do AHU room sizing. So let's start. There's simple steps which we have to follow. First step which we have to follow is we have to find dehumidified CFM through heat load using HVAC software or E20 form. So after using the HVAC software, let's say we got 9000 CFM through heat load calculation. So we have to add 5% safety factor into this one to keep safe side. So in order to add this 5% safety factor, multiply 9000 with 1.05, you will get 9450 CFM. So for this CFM, we'll select AHU. There I have a catalog for air handling unit. It's a double skin modular air handling units provided by this Matco air conditioning. So let's move down and select our air handling unit for that CFM. So let's say we are going to select this horizontal typical configuration air handling unit. Okay, as you can see that this is the liter per second, so you can convert this into CFM. This is our flow rate, and this is the height of the machine, this is the width of the machine, and this representing as length. So if you notice over here for this diagram, here A is representing as fan motor compartment, B is representing as coil compartment, and this C is representing the filter compartment for primary and secondary, and this is you can see that this is the returns duct area, this is the fresh air duct area, and this is the supply duct area. And you can see that E is representing the whole length of this air handling unit. So as we know that how much is the CFM, we got 9450 CFM. If I want to convert this CFM to liters per second, I will get 4459 liters per second, that's around 4460 liters per second. So move back to our catalog. Over here we got 4026 liter per second and 4598 liters per second. So we'll go for the higher side, we'll not go for the lower side. As you see that CFM liter per second we got is 4460, and over here we got 4598 liters per second. So this one is closer, so it's like this one, 4598. So for this liters per second, we got height of machine is 1.4 meter, that is 1400 mm, and width is 1900 mm, that is 1.9 meter. And as I told you, E is representing the whole length of this machine. So if we scroll down over here, this is the E, and how much we got over here is 3.9 meter. So this is our AHU dimensions. Length is 3.9 meter, width is 1.9 meter, and height is 1.4 meter. So move back over here. As you can see, AHU, which we already selected from the approved supply data sheet for our calculated CFM of 9450 CFM. So width we got 1.4, height we got 1.9, and length we got 3.9 from the supply data sheet. So if we will add 1.5 meter in all dimensions of air handling unit, we will get the room size for this air handling unit. As you can see that I have added 1.5 meter in the width, and 1.5 meter in the height, and 1.5 meter in the length. So total AHU room size will be 2.9 meter is the width, 3.4 meter is the height, and 5.4 meter is the length. So this is how you can do AHU room sizing. So I will tell you guys about exhaust Cfm calculation. So there I have a drawing in which I will show you for one of the toilet. As you can see that this toilet, its length is 200 centimeter and width about 130 centimeter. So it's 2 meter by 1.3 meter. This is the area of this toilet. So for exhaust Cfm calculation, we know that the area of this toilet is 2 into 1.3. So it will be 2 into 1.3 2.6 square meters. So as per architectural drawing, we can see the height of the toilet wall is about 3 meters, so it's 3 meters. So in order to calculate the volume, that would be area into the height of the toilet. So as we know that area is 2.6 and height is 3. So 2.6 into 3 will get 7.8 cubic meter is the volume of that toilet. So in order to calculate the exhaust Cfm, we have to use this formula, volume into air changes per hour divided by 60. But this volume, it should be in cubic feet. So in order to convert that volume into cubic feet from cubic meter, we need to multiply it by 35.28 conversion factor. So 7.8 into 35.28 will get 275.18 cubic feet. So as per HVAC standard, for toilet, pantry, kitchen, we are taking air changes per hour is about 8 to 12. So this ACH is basically air changes per hour. So as I told you about from the HVAC standard, toilet, pantry and the kitchen, it's about 8 to 12. So we are going to take air changes per hour over here is 10. So this is the volume which we have calculated above. So we have to use this volume over here, that is 275.18 into air changes per hour, that is 10 for the toilet divided by 60. So how much we will get into 10 divided by 60, that is 45.86 CFM. So this is the CFM, exhaust CFM required for 2.6 square meters area of the toilet. So if you have seen my previous videos regarding duct sizing calculation, can show you over here again by using this Duct Size program. So the flow rate, you know that 45.86, we'll use around 46 Cfm, and head loss, as I told you, 0.06 inches of water column per 100 feet. If you have seen the previous videos, I have explained it over there. So as you can see that we have put this two parameters, flow rate and head loss. We can get the duct size over here. Let's say 6 by 8 by 3, no, 6 by 3, no, 4 by 6, yeah. If we change this one to 4, because we have to keep this in even numbers, so 6 by 4 inches is the good size for this duct. Or if you go for round, it will be 4.9 inches. Oops, sorry, 46 Cfm, 1.6. So it will be around 5 inches. So 5 inches will be round out, will be round off, and it will get 6 inches. So you will use 6 inches over here for that much Cfm. So this is how you can calculate the exhaust Cfm for the. Today I'm gonna tell you guys how to do water balancing, or how many tons do we have to open DRV for water balancing. As you know that DRV is installed on the return side of the terminal unit and used for water balancing purpose. Usually air water balancing in the building is done by a third party, a testing commissioning company. Then they submit the report. As an engineer, we should know they balance DRV correctly or not, because if they balance DRV correctly, we will get the exact design flow rate. So the formula which we are going to use over here is this formula, that is delta P is equal to Q divided by 0.1 into kVs whole square. So what is delta P over here? Delta P over here is representing as signal or differential pressure, and Q is the flow rate, but remember this flow rate in cubic meters per hour, and this kVs is signal coefficient, and we will get this value from the supplier for double regulating valves for different sizes. So this is the formula which we are going to use over here to know that how many tons do we have to open DRV for water balancing. So let's say we got Q equal to 0.75 liters per second. As I told you, this Q in this formula should be in cubic meter per hour. In order to convert this Q into cubic meter per hour, we have to multiply this 0.75 by 3.6. So we'll get how much, we'll see, 0.75 into 3.6. We will get 2.7 cubic meter per hour the flow rate. 2.7 cubic meter per hour is the flow rate we are getting over here. So if we'll put the values into this formula, but before putting the values, we should check the kVs from the supplier data sheets. So let's say that as you can see that this is the chart over here for double regulating valve for different sizes. This is for half inch, this is for 3/4 DN20, this is for 1 inch DN25, and this is for 1/4 DN32. So let's say that we have a pipe size over there is 1/4 DN32. As you can see that over here, what is the kVs for 1/4? It is 16.7. So this is the value which we have to use over here. So let's move back to the formula. 16.7. okay, so 0.1 into kVs, that is 16.7. so we got 2.67. So Q divided by 1.67. Q is 2.7 divided by 2. How much we got before? 0.1 into 16.7, 1.67. Now we have to give the square root of this one. So if we'll get the square root of this one, we'll got 2.6 answer over here. So delta P we got over here is 2.6. So what does that 2.6 means over here? That means we have to open DRV 2.6 tons to balance the water through that DRV. And let me tell you over here why water balancing is important. Water balancing is important to ensure that chilled water system deliver correct flows to all terminal units in our HVAC circuit, and so that our control valve will work properly, which in result correct output of the energy to the space. So this is very important to do the water balancing. So this is how you can check how many tons do we have to open DRV for water balancing in terminal units and coil units here. In this video I will tell you guys how to calculate the chilled water pipe size. So let's start. But before starting I want to show you something over here. I already explained this thing in the previous tutorial, but I will explain you again. In the case of district cooling, we are using 1 TR is equal to 1.5 GPM, and how this comes by using this formula. TR is equal to 24 GPM divided by delta T. So in the case of district cooling, we are normally maintaining delta T of 16. So if we are going to use delta T 16 over here in this formula, so we will get 1 TR is equal to 1.5 GPM. That's the case of district cooling. So same formula we are using over here. If we are using chillers, so delta T will be 9 to 10 degrees. So by using this 10 degrees over here in this formula, 24 GPM divided by 10, you will get 1 TR is equal to 2.4 GPM in a case of chillers. So let's start this pipe sizing over here. There I have an HVAC drawing. I'm going to do the pipe sizing for few pipe segments over here. So before doing that, I will show you a schedule over here for all the FCUs. As you can see that this is total capacity in MBH, airflow in CFM, water flow GPM, and ESP in pascals, and motor power, unit dimension, everything. So let's start with this machine, corridor machine. As you can see that its serial number is 3FBL2. It's a corridor machine, ducted unit, and its MBH is 29.39, and CFM is 1049, and GPM is 3.67. So let me show you how this GPM comes out before start the pipe sizing. As you can see that 29.39 MBH is the heat load for this corridor machine of 3FBL2. So 29.39 MBH is the heat load. If we divide it by 12, we will get the tonnage. So 2.44 ton for this machine. So if we are going to calculate this GPM, how this comes out, as I already explained you over here, we are using a district cooling system over here. So how much GPM is required for 1 TR? It is 1.5 GPM is required for 1 TR, and we have a machine of 2.449 TR. So we need to multiply this tonnage with 1.5, so we will get the GPM. As you can see that the GPM is required for this machine is 3.67 GPM. You can see that 3.67 GPM. This is how you can calculate the GPM for each and every machine. In the same way you can do for other machines like Orchestrum 19 with 19.47 GPM. 19.47 is the MBH load. divide by 12, you will get the tonnage, and if you multiply it with 1.5, you will get the GPM. That is 2.43 GPM is required for this machine. Over here you can see that 2.43 GPM. So let's move to the pipe sizing now. So I'm going to do for this corridor machine 3FBL2 corridor machine. Over here you can see that this machine is 3FBL2 corridor machine, the one I was talking in the schedule. So you can see that we already calculated the GPM for this machine, and the GPM required is 3.7 GPM. For our calculated heat load, GPM required is 3.7 for this machine by district cooling system. So now we are going to see how this 3 by 4 inch pipe size is coming for this 3.7 GPM. So let me open this pipe sizer tool. So I have opened this pipe sizer. As you can see that we are using a black schedule 40 pipe over here, so we have already selected over here, and the fluid is at 50 degrees Fahrenheit water. So now we are going to check the pipe size required for 3.7 GPM. So if you can see that, but before starting this, I want to show you one thing, a design document, because we are going to do this as per our design document. So let me open this design document, general mechanical notes. These are the general mechanical notes. You have to open this and see what is the pipe sizing criteria mentioned over here. As you can see that for pipe sizes up to 50 mm, velocity of the water should not exceed 1.22 meters per second, and pressure drop not exceed 600 pascals per meter. And for pipe sizes 50 mm up to 200 mm, pressure drop should not exceed 400 pascals per meter, and velocity not to exceed 2.4 meters per second. So this is our limitation for do the water pipe sizing. We have seen this from our general mechanical notes. So we are going to do the pipe sizing as per this limitation. So whenever you are doing the pipe sizing, you have to keep this thing in mind. So let's move to our drawing. As you know, this machine has 3.7 GPM. So let's move to this pipe sizer. If we are using this half inches pipe size, and with the we are getting 1.4 US GPM over here. So if we are using our GPM, that is 3.7 GPM. As you can see, the fluid velocity is 3.91 feet per second. This is the calculated fluid velocity, and the head loss is 15 feet per 100 feet. As I already told you, our design document from the general mechanical note, it says if pipe size is less than 50 mm, velocity should not exceed 1.22 meter per second. If you convert this velocity in a feet per second, it will be 4 feet per second, and a pressure drop will be 4 feet per 100 feet. So if we move over there, fluid velocity is almost in the border, that is 3.91. Actually it is less than 4 feet, but head loss is too much, that is 15.039. that is not acceptable. So we are going to check 3-4 inch pipe size. If we use 3-4 inch pipe size and our GPM is 3.7, so we are going to use 3.7 GPM over here. As you can see, the fluid velocity now 2.23 feet per second. That is less than our specified fluid velocity, that is 4 feet per second from our this general mechanical notes. So fluid velocity is okay. Now move to the head loss. If we go for head loss, it is 3.757 feet per 100 feet. As I told you from design document, it is, if you convert this, it will be 4 feet per 100 feet. So head loss should be less than 4 feet per 100 feet. As you can see that this is 3.757 feet per 100 feet. So the pipe size which we have selected, 3-4 inches for 3.7 GPM, it is in the safe range. So we are good to go with 3-4 inch pipe size. You can also use this friction loss chart for floor piping system to check your friction loss. Let's say our GPM was 3.7 GPM over here. This is the flow rate, this is the head loss, and these are the pipe sizes over here. So our flow rate is 3.7 GPM, that will be below 4 GPM over here. And if we move to 3/4 inch pipe size, if this 3.7 GPM cross over here 3/4 inch pipe size, it will fall somewhere, it will fall over here just before 4, that may be 3.7 3.8 feet per 100 feet. So as you can see that we already checked over here, and the pipe size head loss is 3.757 feet per 100 feet, that is less than 4 feet per 100 feet. So we can use this pipe size 3/4 inch for 3.7 GPM. So let me show you one more over here. Okay, let's do a pipe sizing for these two pipe segments with the 22.9 GPM. Okay, go to the pipe sizer. If I select 1 inch 1/4 pipe size, and I am going to use 22.9 GPM, you can see that fluid velocity is 4.91 feet per second. That is more than 4 feet per second. 4 feet per second is our design limit. So, and also head loss 8.33 feet per 100 feet, that is more than 4 feet per 100 feet. So we are not going to select this pipe size for 22.9 GPM. Let's move to the higher side, that is 1.5 inches, and give our GPM 22.9 GPM. As you can see that fluid velocity is 3.61 feet per second and head loss is 3.874 feet per 100 feet. You can see that fluid velocity 3.61 is less than our specified fluid velocity, that is 4 feet per second, and head loss of 3.874 per 100 feet is less than our 4 feet per 100 feet. So we are good to go with this pipe size of 1.5 inches for 22.9 GPM. So if in the same way you can do the pipe sizing for other pipe segments, and you can use pipe sizer tool to calculate the pipe size. In this video I will tell you guys how you can calculate duct size using the Duct Sizer program. So there I have opened a Duct Sizer program provided by the Handbook. So for the duct sizing, you must give this input like flow rate and the head loss in order to get your duct size. So for example, from the heat load calculation, I have calculated CFM 600, like 600 CFM for the particular room, and I want to calculate what will the duct size that is coming out from the machine. So for this purpose of 600 CFM from the supply data sheets, let's say we have selected a ceiling ducted fan coil unit, FCU. So if we will go and give our CFM of 600 over here, and we move to the head loss of second input, just keep in mind that for the head loss for the fan coil unit, it should be less than equal to 0.05 inches of water column per 100 feet. So this is your design value for the head loss. Head loss should not exceed 0.05 inches of water column per 100 feet, so that you will not get noise issues in your duct. Okay, we give this input of head loss 0.05 inches of water column per 100 feet. Now let's move to this duct size, and if we'll say 1 over here, and it will give the value for the other. For example, this is the width and this is the height. If I will change this one to 10, let's say 10 is the width and 15 is the height. So one thing you need to remember that for the duct size, you always need to get even numbers in the duct size. You will never see the odd number in the duct size like 13 inches by 15 inches or 9 inches by 15 inches, because this is a standard, so you always have to use even numbers in the duct. And second thing, you have to keep in mind aspect ratio during duct sizing. What is the aspect ratio? Aspect ratio is basically width to the height of the duct. And what is the best aspect ratio? Best aspect ratio is 1:1. Let's say our duct width is 400 and duct height is 250. So I told you aspect ratio is width to the height of the duct. So width is 400, height is 250. Let's say 400 divided by 250. So what's the aspect ratio? 1.6. So that's not bad, that's good. And what is the maximum allowable aspect ratio? Maximum allowable aspect ratio is 4:1. Don't exceed this more than 4, because if you will exceed more than if you exceed 4, then what will happen? You will get noise issues and more friction losses inside your duct. So maximum allowable aspect ratio is 4:1. So let's move and change this size to 12. As you can see, 12:12 we are getting the 1:1 aspect ratio. But one thing more you need to see over here, this is the calculated head loss, that is 0.05 inches of water column per 100 feet. And what is our specified? 0.05. So just keep in mind this calculated head loss should be less than our specified head loss. So we still need to change the duct size over here. So what we will do, we'll change this to 14. Let's say 14/10. 0.05 is still more than this, so we'll change this to 16/9. So we don't want an odd number, as I told you before. Standard we have to give even number. So let's change this one to 10 inches. So this is the 600 105. Let's change this one to 10. So as you can see, the head loss calculated over here is 0.04, that is less than our specified head loss, 0.05 inches of water column per 100 feet. So this duct size is perfect to use over there. So what would be 16 inches by 10 inches? 16 inches, that is 400 mm, and 10 inches is 250 mm. So what would be the aspect ratio in that case? 400 divided by 250, that is 1.6. So aspect ratio is good, no problem. But sometimes you have to play with this aspect ratio because of the ceiling height issues. Sometimes ceiling height is very less. For let's say the ceiling height is 500 mm. So you will keep your duct height maybe restricted to 200 mm or 250 mm, because you need to give space for the other services to pass through. Like if any sprinkler pipe is passing over there or any chill water pipe passing over there, you need to give space to that service too. So, and from here you can change the units too, from metric to IPS US units. So this is how you have to you can calculate duct size using a duct sizer program.